In this video, we are going to be covering the different positions that things can be during their orbits, like let's say the moon around the Earth or a planet around the sun. So we're going to be covering moon phases, planetary positions, and synodic periods. Let's start off with basic moon phases. If we say the sun is on this side and the Earth is over here, the light will always hit the moon on this half of it, right? So the moon will look like this throughout, but from an observer on Earth, that'll look different, right? So if we see the moon from here, we will always see the back of the moon, and we'll see this phase called the new moon. After it moves a little bit, maybe over here, we'll see a tiny sliver of the moon, and it'll start to grow, and this is called a waxing crescent. Here the Earth is viewing the moon from this angle, so we get this little sliver over there. Next we have first quarter. This is when exactly half the moon, even though it's half the moon is full, we call it a quarter because it's a quarter of the cycle. So this is half the moon is lit up. We see this portion right here. Then the waxing gibbous is just like waxing crescent, except it's a gibbous because it's more full, and we'll see this portion. Then we see the full moon, where it's exactly on the opposite side of the Earth. So like the sun is on one side of the Earth and the moon is on the exact opposite side. Then we have a waning gibbous, which is this much. We'll have last quarter, which is 3/4 of the way through the moon cycle. Then we have a waning crescent. And then we circle back to the new moon and start all our phases again. Just a couple things to keep in mind. Whenever the lit up part of the moon is increasing, or it's going from a new moon to a full moon, we call that waxing. We're adding more to the moon every single night. And then when the side of the moon that's lit up is slowly shrinking and going away, we call that waning. Now let's move on. Let's talk about planetary configurations now. So just as the moon had different positions being labeled differently all around here, there's many names for planets in their specific positions as well. And there are going to be 8 main positions we're going to be talking about. 4 of them are for inner planets and 4 of them are for outer planets. Inner planets are defined as ones that are closer to the sun than the Earth, and outer planets are ones further away from the sun than the Earth. We have that labeled as orange for the inner planets and blue for the outer planets. Okay, let's start labeling. If an inner planet like Mercury or Venus are exactly between the sun and the Earth, this planet, it's said to be in inferior conjunction. Now a planet on the opposite side, so if the Earth and the inner planet is on opposite sides of the sun, we call this superior conjunction. Okay, now you see that there's a position over here and over here, and these aren't just random positions. There's a very specific way we get this far. If we take the center of the sun, the center of the Earth, and we make a triangle with the center of the planet, you can see here that this angle is exactly a right angle, and we get a right angle triangle right here. This is because this line coming from the Earth is tangent to this circle, and whenever there's a radius of a circle and a line tangent, that always makes a perpendicular intersection. We can do the same thing over here and make another right angle triangle. These positions are called greatest eastern elongation, and the one over here is called greatest western elongation. Now this might seem a little confusing because we have north, south, and east and west should be on this side, but here it's switched. We have west and east, but that's the way it's defined, and that's something we have to keep in mind, that when we're talking about planetary configurations, we have our western on this side and our eastern on this side. And this has to do with the perspective we're looking at it from Earth, which kind of flips the entire board. Now let's go to the outer planets. Similarly down here, something that's completely opposite from the Earth, we call this one being in opposition. So it's on the opposite side of the sun from an observer on Earth. And we call the one across the sun a conjunction. Just like we had east and west making right angle triangles here, we can do the same thing. Let's draw a point from the center of the sun to the earth, and this time the right angle happens at the earth, not at the planet. We have a right angle right here, and we can do the same thing and make a right angle triangle right here. It's flipped now, where before we had a right angle triangle coming from the planet, we have it with the earth because that's the only way we can make a tangent line with the radius of a circle. Let's label these positions now. So this one is called western quadrature, and this one is called eastern quadrature. And there we have it. These are 8 different positions that planets can be at. So just to review, we have inferior conjunction and superior conjunction for inner planets. We have greatest western elongation, greatest eastern elongation. And now moving on to outer planets, we have opposition, we have conjunction, we have eastern quadrature, and we have western quadrature. It can be a little tricky to memorize all these positions. If you want, you can also make flashcards, whatever helps you. But it's usually helpful to get these positions memorized, especially because there's only 8, and a lot of them are intuitive, like opposition being opposite to the sun, or inferior and superior conjunction. One is closer to the earth, one is further from the earth. But if you have these positions memorized, these terms will make a lot more sense when dealing with planets. But for now, let's move on. Let's talk about some angle conventions. So when we have a triangle, let me actually draw one out. So let's say we have a straight line here, and then we have a 90-degree triangle over here. This is 90. Let's call this is the sun, this is the earth, and this is the planet, let's say. There are specific conventions that we use to address these angles. The one at the sun is usually called theta. The one at the earth is usually called phi for phase angle. And the angle for the planet is called eta. So we have theta, eta, and phi. Let's write this down. Another term you can use for this one is the angle of elongation, and this one is the phase angle. So these are conventions we should keep in mind when we discuss triangles like this, so that we all know what we're talking about, we're all on the same page. But now let's move on. Synodic period. This is what I was talking about in the beginning of the video, and we can only use this if we assume that objects are in circular orbits, like maybe there's a satellite going circular around the Earth, or maybe a planet going circular around the sun, and we can approximate that. And the objects have to be in the same plane of rotation. Just as a reminder, when we have our sun in the center of our solar system, every single planet that orbits around it are almost on the exact same plane. So it's all flat. If you've ever seen a solar system model in like 3D, maybe in your science classroom, you see all the planets that are lined up, right? That's almost what it looks like in real life as well. The synodic period formula is the synodic period, which is S, equals 1 over the period of any planet minus the period of the Earth. And here I put planet and Earth. You can pretty much put anything you want, and let's discuss how this can be used in a problem. So this one will also cover a bonus topic, but before we get to this problem, let me just draw like a scenario. So one more time, if we have the sun here, and we have maybe the Earth over here, and let's say we have Mars over here. Obviously, Earth and Mars are rotating at different speeds, right? But the synodic period tells us that if we start off Earth and Mars at in this position, how long will it take to get the Earth and Mars back aligned up perfectly in a straight line? Or in whatever position they were before, you want to circle back to the exact same position. How do we do that? So maybe the Earth moves here by the time Mars moves over here. Maybe the Earth will move here by the time Mars gets over here. It's pretty hard to keep track of. What the synodic period basically does with this math, we are basically holding one object at a fixed position. And we are saying what is the time it'll take for Mars to go completely around, holding whatever the other object is in one position, but letting Mars, or the second object, move around the Earth in this case, with respect to the Earth. So it's not the actual speed of Mars, it's with respect to the Earth. From an observer on Earth, what does it look like that Mars is rotating around the sun? That is what this formula allows us to do very simply. So we don't need to keep track of all the complicated math and the different velocities that show up. A very abstract example of this would be this problem here. What is the synodic period, and there's a typo in this problem, what is the synodic period of the Earth if it rotates around its own axis in 23 hours, 56 minutes, and 4 seconds, while going around the sun in 365.25 days? Now, the first question that might come to mind, and this is our bonus topic, is shouldn't a day be 24 hours? Let's just say the sun is over here, and then the Earth is orbiting over here. The time it takes for the Earth to go around its own axis once is almost exactly 23 hours, 56 minutes, and 4 seconds, which is 4 minutes less than a day. The 24 hours that we get is accounting for the time it moves during those 23 hours and 56 minutes. So by the time it takes a full rotation around, the Earth has obviously moved a bit in its orbit, right? So let's say the Earth faces this way initially. If we wanted to rotate around, and taking into account that it moves a little bit, the Earth will face again this way. But the sun is not exactly over here, it's over here, right? So the extra 4 minutes we add by taking into consideration the time it moves to face back to the sun. And that is a full 24-hour day from a person on Earth to see the sun in the same position in the sky again. This is why each night's the stars are moved a little bit. Like if I look up at the sky at 12 at night today, I will not see the same sky 12 at night tomorrow. It'll be shifted a little bit. If I look back at the sky exactly 23 hours, 56 minutes, and 4 seconds from now, the sky will look exactly the same. This time over here, the 23 hours and 56 minutes and 4 seconds, this is called a sidereal day. And this day is defined as the time it takes for the Earth to rotate back again and face the same position relative to the stars, not relative to the sun, because we move a little bit with respect to the sun. Our 24-hour day that we know and we're used to is not the one we were working with in this problem, which is 24 hours. And obviously this 0.25 of a day accounts for every 4 years we have a leap year, right? So that's why a year is that many days long. Let's just plug these numbers into the formula for now. But before we do, we need to make sure that these are in the same units. So let's turn everything into hours. How about that? So the 23 hours and 56 minutes, 4 seconds, we can say rotation takes, and how would we calculate this? We can do 23 plus 56 over 60 plus 4 over 60. Let's take a bit to think about why did I write it like this. So this 60 converts this to minutes, so I can add minutes and minutes. This 60 converts the minutes into hours, so I can add hours and hours, right? From our calculator, we get 23.934 hours. So now a revolution takes how long? And a revolution is the difference between a rotation and a revolution. Rotation is around its own axis. Revolution is around the sun, giving you a full year. This one will take 365.25 days into hours. From my calculator, we get 365.25. So the number of days times hours in a day gets us 8,766 hours in a year. Let's find the synodic period, which is going to be 1 over 23.934 minus 8766. And from our calculator, what we can do, cut out what we can do. And this might be a little tricky to do on a calculator, so let me just show you what I'm writing. My first step is to subtract the two fractions. Next, once I get my answer, there's a button over here that can inverse it. So once I inverse my answer, I'm going to press enter. This is my final answer. So from our calculator, we get that the synodic period is 23.999, which just rounds off to basically 24 hours in a day. So when we take into account the period of Earth rotating around its own axis and the revolution it takes for the Earth to go around the sun completely, we get the 24 hours in a day. So this is another way to define it. So to review, we talked about the phases of the moon, planetary configurations and the 8 different ones for outer and inner planets. We talked about angle conventions and how you can use, if you have a right angle here or a right angle here, you can use trigonometry to find missing lengths and missing angles. And then we talked about synodic period. That can only apply if objects are in circular orbits or if they're on the same plane of rotation, which the Earth revolving around its own axis and going around the sun, they're both circles and they're both on the same plane of rotation. I'll see you in the next video. As always, thank you so much for watching. The notes that I used during this video is linked in the description for you to refer to and use in the future. And please be sure to check out the rest of the videos in this series. I'll see you in the next one.